Wow. Earlier, LeetCode was not working. I had to force myself to take a break. Where are we? Here. Get rid of that. Okay. Remove all adjacent duplicates in a string. This should be a fun video. Everyone is, not everyone, not Nicole. Where's Nicole at? Okay. Anyway, I'm gonna put this somewhere else for the next how long? It is 8:40. I did some more editing, went to the gym, did not DoorDash. So this video is about code, and I'm literally doing a bunch of other stuff. Let's say I did an open play, I went to the gym, got shampoo. I didn't finalize edits, but this will be done soon. And then I think I'm gonna work more on the open plat tonight. Yeah. Anyway, phone in the other room, at least for the time being. Make sure it doesn't fly off the rails or anything. Need water. You know the rules. You know the rules. You know the rules. All right. Let's get straight to it. Let's get right into it. My head itches. I need to shampoo. I need to shampoo. I was out of shampoo for a couple days. Big sad. But we're here and we're focused on the next 30 minutes. Where the frick is my timer? Thank you, sir. And we start now. Remove all adjacent duplicates in a string. What the hell does that mean? So you're given a string S consisting of lowercase English letters. A duplicate removal consists of choosing two adjacent and equal letters and removing them. We repeatedly make duplicate vowels on S until we no longer can. We repeatedly make duplicate removals until we no longer can. Return the final string after all such duplicate removals have been made. It can be proven that the answer is unique. It can be proven that the answer is unique. Okay, so A, B, B, A, C, A. Example is C, A. Why is it C, A? For example, in A, B, B, A, C, A, we could remove B, B since the letters are adjacent and equal. This is the only possible move. The result of this move is the string AACA, which only possible move is A. Okay. All right. Okay. So given A, B, B, A, C, A, what's our approach here? Well, the desired output is CA. Okay. And in terms of English, we do a duplicate removal of B and B, which leaves us with a new string of A, C, A. And because we, I guess, are not done, we remove AA as well. And then we check again, CA is the final answer. Winner, chicken dinner. Okay. How do we translate that into code? Well, iterating over a string is necessary. And removing, I guess we can say, okay, let's look at it this way, right? We can iterate over the entire string, right? And we can build a new string that consists of none of the duplicates, correct? So, but it could make another string that then consists of duplicates. And basically we kind of, I guess, without saying it, but saying it, we kind of recursively go down. So there's some function, we pass in this string, right? And then within that function, it calls itself if there are, well, no, it calls itself anyway, and we have a check. This is kind of recursion, low key. It's recursive. It's recursive. That's the tick I'm getting. So let's take a look. So we call some function f, or remove duplicates. We pass in a, b, b, a, c, a. It removes b, b, and any other existing duplicate removals, right, that exist in the string. And then it calls f on the resulting string, which is a, c, a, which we know here has a duplicate, but this function does not. Then it calls again f on ca, and it knows that there is no duplicate. So what's in that function? Well, there's first some code to find, and I'll say remove duplicates, right? So some code to find and remove, and then the resulting string from the find and remove algorithm then gets passed into f, and then we just return the string that's left over. Then we just return f of, and f of can return what? Whatever string comes out. Okay, so let's start with the first level. So what's our duplicate finding algorithm? Well, we just take an empty string, call it whatever you want, right? And the case is if this letter is equal to the next letter, we remove it by simply not adding it to our result string. So we'd say if a equal to b, we're going to add it if it's not equal. So we'll say if not let equal next, then append that to our string. So for example, a is not equal to b, so we append a to our string. We say b is equal to b, we don't add it. We skip two places. Then we say is a equal to c, we add a. Is c equal to a? No, so we add c. And then we're at our last, there is no next. Okay, so there is no next, so we just add this. So that looks like a while loop, right? So we say something like while we have a valid pointer, a valid index in the character array or string, continue to make those checks, and then basically we'll do a check to say like if there are two characters left, else we know that pointer probably now points to the last index, and therefore there can be no additions. Well, basically we just say this. We know that if there are two characters left, right? If two characters left, then just append the last two characters. If there are two characters left, what am I saying? We can't add them in pairs though. Not really. In the last case, yes. But we can't really add them in pairs. So there's a special case for if we hit index 0, 1, 2, 3, 4, and 5. So if we hit index 4, with two characters left, right, and let not equal to next, then just append the last two. Otherwise, you can say else for now. Else if let, you can say else if let current letter not equal to next letter, then append that letter. Then say plus equals let, okay? So this should return our proper string, okay? Let's walk through it just one more time. So we have some pointer, also called PTR, equal to 0. We say pointer equal to 0. We're gonna do a while loop, looping to the length of, I'll say length, wow. Length of s, what, -2? Yeah, -2 looks good. Or, we'll say less than -1. Yeah, I feel like that's convention. I feel like that's part of the pattern for coders, okay? So pointer gets incremented at the end. Little code here, pseudocode, but really not pseudocode. Okay, we say what? We say if 2 characters left. Okay, so if 2 characters left, if 2 characters left contains good enough logic to avoid collisions. Let's just say that for now. So there are not 2 characters left. There's way more than that. Then we just compare if let equal to this, then our string goes to if not equal to next, then we just do A. Oh, interesting. Okay. So I just discovered a bug. Okay. So pointer gets incremented once. Now pointer points at B. If this properly skips this, B equal to B, yes, it is. What does that mean? That means don't add it and move pointer up 2 spaces. Now, why is that valid? We can only enter this loop if we are less than -1, which puts us at 2, right? And we'll check other cases and see if it's actually working. But I think that's pretty cool. So in this case, it was, so pointer gets a +2. So in the case of it's not equal and we're appending, pointer moves up one space. In all other cases, it moves up 2 because I think it's probably equal. So because index 1, which is B, equal to index 2, which is B, we skip, make pointer, it was 1, now it's 3. And then we do the same check. We add A, we add C, we add A. Now, pointer was 3, and then it was 4, which means that if we properly check, right, if there are 2 characters left and they're not equal to each other, append the last 2, which is C and A, and then pointer, I guess plus equals 2. Or I guess that just happens anyway. In that case, pointer becomes 6, which is definitely not less than 5, and then it exits, and we just call the function on that. All right. Now let's try a different example with more stuff. See if we actually got this right. We try one from there. I'm gonna append another one on the end. I'm gonna add a CC to the end. Okay. It's now index. It's now length 8, but last one's index 7. So we're gonna loop until we are at 6, index 6, I guess is the max. Anyway, pointer points to 0, and we say same logic as before, but we're gonna go all the way to A, C, A. We'll get to the C, which yes, there are two characters left, right? But they are equal to each other, so we just increment by 2. So we got to the 6, increment by 2 becomes 8. Okay. So I mean that sounds like looks like it works. I'm gonna go off that because we're running out of time. It's 18 minutes left over. So let's see. So pointer gets 0, and we'll say while length of s. I'll say while PTR less than length of s -1, right? So we just write some pseudocode to say if 2 char left, and I'll say cur not equal to next, right? Then we say, I guess answer. Answer plus equals what? Cur. That's a join of next. Is that even right? Else, else if cur, if what? If not cur. Then we just append the current one. So we just say ants plus equals plus cur. And we say, wow. And we say ptr plus equals 1 plus equals 1. Then we say at the end of this loop, ptr plus, I shouldn't say that either. Well, that's stupid. Oh, okay. Find another bug. So maybe it's always a +1, which is actually a +2 if we skip, right? Okay. So how do we know if there are 2 characters left? Well, we know that a pointer is equal to 4 from our old example. We know that that's, so what is that? What's in relation to that? Well, 4 is 2 less than the length. So we say a pointer is equal to length of s minus, I guess, 2. So pointer is equal to length of s minus 2. And, right? So we can write in, I'll call it nxt. Square gets s at ptr. nxt gets s at ptr plus 1. All right. At the end of this, we just return what's our base case, right? It's it's recursive. So I guess the base case, usually start with the base case. I didn't start with the base case. So we'd say return. I mean, there could be a contains duplicate function that just checks if it contains duplicates. The removal doesn't remove anything. It just doesn't append everything to the list. So so how do we check for, what do we want to stop? We want to continue to remove duplicates so long as there are duplicates. So we can say if the set of S is, what's the set? What's that return? I'm trying to compare if the set is what? Oh, okay, I got you. If the length of a set of S is equal to the length of S, then we just return S. So what is that comparison? Well, set is it's a unique collection. So once we get down to once we get down to CA, the set of CA is CA and the length is 2. The length of CA is 2, therefore we're going to return S. So we're then return self dot remove duplicates S for answer. try it out. Let's try it the frick out, man. I'm not even gonna run it. The goal is to be able to run it, but in the interview you can't always run the code. Like when I did my Amazon interview, I literally just had like an editor, and they would just like the interviewer kind of knew what my code did. I was like, how do you know? Like, how do you I had no practice. I didn't know that you could. I didn't. Well, I knew that, but I just when you rely on coding tools in the day job, interviewing is about knowing how your code works without the tools, without the automatic run and run your test, right? So we've got this function. I'll say f of a, b, b, a, c, a. We initialize a pointer, move some stuff around, and essentially the output should be, well, the algorithm we did works, right? So therefore, I mean, this is running. Let's run it. See what happens. Wrong. AB cur plus nxt. Maximum recursion depth exceeded. Seriously? Will it print S if I give it to it? Print. Yeah. What is S when it comes in? Tell me. It can't. It probably can't. A good test would be to see if we get the right answer from the next one. That was my original code, though, was it? Let's not do this, and let's just do return empty string. Let's print out ants. I should do more diligent debugging, but to answer, notice A, B. Ooh, okay. What didn't I count for? So at the end of this, answer was A, B, A, C, A. How? Pointer should move from 0 to 1 to 3, right? It should move from 0 to 1 to 3 to 4. 0, 1, 2, 3, 4. Okay. So we get the ends on 4. We shouldn't hit 3, or we shouldn't hit 2. Why do we hit 2? 0, 1, 2, 3, 4. Okay, what? Oh, I forgot. There's a couple. I missed a key. I missed a key step. So basically, if there's 2 left and they're not equal, this 2 left thing is kind of weird, but I think we need it. 8 minutes left. Wow, this really flew by. Jesus Christ. Where are we at? So when it got to 1, what did it do? Cur was B. Next was B. If there's 2 left and they're not equal, just add both. Move it up 1. Oh, so that means that they must be equal here. What am I doing? Yeah, I didn't do that. So the case was, I did it, but I just what I meant to do. So if there are 2 left and they're not equal, it is properly adding them and moving the pointer up 2 spaces. That's good. If they're else, so there's another one. So if we're not at the 2 marker, when there's 2 left, there's 2 things we can do, right? When there's 2 left, we can say if cur equal next, then we know, well, we know if they're not equal, we know if cur not equal to next, then we just do this. Which is basically what I just had before. But we didn't get the simple case that if there are more than 2 left, and cur is not equal to next. Then if they're not equal, add it. If we got to this part, oh, okay, I see now. So if we get to out of this, the branching here, that means that cur is equal to next. And if cur is equal to next, and this is bad, I hate this, this smells. Right? That directly solves our problem. But there's a greater bug in the logic. There's a greater bug in the logic. Case 1 passed. No way. Case 2 did not. We took out an A, Y. So there was, let's look at what was the answer the whole time. How did the answer get built here? Answer was empty, then it was A. It was AZ, 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 A. What the fuck? Oh. A ants gets ants plus cur plus next. Still outputting AY. What? Well, maybe it's not that complicated. Maybe we're making it overcomplicating it. I have 3 minutes left to deconstruct what I did. So we're looking at it in pairs, right? We're saying there's A, B, B, A, C, A, and we're comparing and we're sliding this thing over. Oh, it's a sliding window problem. It's a sliding window problem. I forgot the format for sliding window. I did forget the format. And I don't think, well, it's recursive because we have to run the same code again and again. But, okay. Anyway, it's recursive sliding window. So our windows looks at A and B. If they are, so there's 2 cases, right? Equal and not equal. If they are equal, they're to be removed, and we move our pointer, which is at 0, up to 2. Okay, but they're not equal. So our pointer moves up 1, and we add A to the answer because that means it's valid. But B, for window gets moved, right? Our window now captures B and B. So because they are equal, we move it up 2 to 3. right? And then we don't add anything yet, because then A is not equal to C, move it up 1. So let's write that logic out simply, right? The simple logic is if cur equal next, or nxt, then we move our pointer up 2 spaces. Else they're not equal, so answer plus equal cur and the pointer moves up 1 space. Okay, that's all. That's literally what we want to do now. Oh, plus equals 1. A minute left. Okay, so how does that break our solution? Well, pointer. Why is there an error here? Okay, good. Okay. So do we need to care about, let's run the code, right? Output. Wow. It was, what? Hold on. Let me make it run one time. Blank A. What? Print cur and print next. I'm out of time, aren't I? Fuck. We know what it is after the fact. I'm just trying to figure out. I think I'm close. Oh, oops. Rookie mistake, brother. Cur next is A, B, A, B, B, A. Okay, good. Wait, okay, yeah, so we're fine. Okay. So we're getting the right answer, right, which is good. So there's one more scenario. And what's that? So if they're equal, we'll skip. If they're not equal and there's 2 left, this branching here, yeah. So that means the next, I guess, else if is going to be, so same thing, right? So the first one didn't pass. So we know it's not equal. That means we know that PTR. Okay, so in this case, okay, so we did that. I guess we can just do that. Yeah, no, that's fine. Yeah. So PTR equal length of S minus 2. If that's the case, the answer gets cur, and answer gets NXT. Right? Else there's more than 2 left. So why did this one fail? Okay, interesting. So there are 3 levels. We got rid of XX, which made it ZZ. And then for some reason, it removed. So pointer in this case, so why didn't it get the... Okay. So what happened here? So S in this case is 4. Pointer starts at 0. So pointer would have to be equal to 2. 0, 1, 0, 1, 2. 2 is less than 4 minus 1, 3. Okay, so we get in the loop, which is good. I'm gonna say if, whoa. I say hi, but I'm really interested in, let's see if that works, right? If as a, so hi twice. The loop runs twice, okay. Let's print something more useful, like cur and next. And pointer, why not? Pointer's 1 and 0, compares A and Z. Then it's at 1, compares Z and Z. Bumps up 2 to 3. Ah. This is stupid. Yeah, that doesn't solve anything. So do we really want to move it up 2 spaces? I can just look at the answer too. Do we really want to move it 2 spaces though? And recursion memory-wise is terrible, so recursion is just ugly. Oh God. Dude. Yeah, I should try it out on a different example. I'm trying to think what's the bug here? Well, moving it forward 2 is not. Moving it forward 2 made sense in the last example. Moving it forward 2, does that always make sense? No, moving it forward 2 doesn't always make sense. Quite simply, if they're equal, just don't add them. But if we want to get rid of both, we can't have the 1b though. So the whole algorithm must be flawed then. Forget it. Let's take a look what happened. Replace. Literal replace. One could use here the standard replace function. This consists of English. I could do that. Generate the list of the hash. and replace them with empty characters. Introduce some new duplicates, for example, AA. Okay. Generate a hash for all 26 possible characters, and then do initiate one step before. Well, previous link. Set one step before length to be equal to the string. What? That made no sense to me. Oh. O of n squared, O of n space. There's a stack. There's two solutions, okay? So this one says, because we have to do it a certain number of times, right? So if we reset this to be -1, then we say while because the length could be 0. They'd be a while loop, okay? So -1 is the start. Then we set it to be length of s for D in duplicate. So if we had A, BB, AC, it'd replace BB with blank. So prev gets -1, not equal to what, 7? Not equal to 6. We say prev length gets 6. Since s gets modified, then we say 6 not equal to length of s is now what, 4? And then replace the AA with blank. That was 4. So now 4 not equal to 2. Well, no, what? What am I saying here? So first -1 not equal to 6. Not equal to 6. Then we set prev length to 6. Then we modify s, and now its length is 4. So previous length was 6, not equal to 4. Okay. Then we set it to 4. Update the length to 4. Move it. Now it's 2. Something got removed. So now 2 not equal to 4. Update to 2. Remove it. It's still 2. Exit. Okay, let's just, yeah, that makes sense. I'm gonna just submit this, and then we're gonna look at the other solution with the stack. What was I trying to do? Recursion? Oh my god. I think it could have worked. I hate to import something, I guess. Did I miss something? They use a capital S. Weird. This has a time limit exceeds. So you have to use the stack version then. Seriously? Okay, crazy. So you can't even use that one. And we say, so we could trade extra space for speed. The idea is to use an output stack to keep track of not only, Okay, that's what I was trying to do. Not stack, but current string character is equal to the last element in the stack. Pop that. Oh, the current one's equal to the last. Wait. What do you mean? What's the stack? What? The idea is to use an output stack to keep track of only non-duplicate characters. Okay. So initiate an empty output stack. Iterate over the string. Current element is equal to the last element in the stack. Pop last element out of the stack. Oh, the string is a list. We're iterating over. We're saying that, but it's empty. So current element, so L or A equal to last element. No. What? Oh, okay. So the last element stack is none or empty. So I like stacks. Stacks are cool. I like stacks. I use stacks so I can. All right. So we have a stack here, empty. Is A equal to nothing? No. So pop add A. Is B equal to A? Add B. Wait, the last element in the stack. Is B equal to B? Yes. Then pop the B off. Is A. Wait. What? So it says current element, which is A, equal to nothing? No. Add the current element in the stack. Add A. Cool. Is now B equal to A? No, add B. Is B equal to B? Pop the last element off the stack. Oh shit, that's crazy. Is A equal to A? Yes. Is C equal to nothing? Okay. That's nuts. What? That's such a clean solution. Why didn't I think of that? That is so freaking clean. Like, what? That's the kind of thing I want to come up with. And it's so fast. Okay. Stack. String. That's all I want to put there. That's crazy. No, for real though. Dude, what? I did not. I need to shampoo my hair like tonight if I can. Oh my god. Okay. Well, we gotta start going back and going through these problems because I'm like, what? I look terrible on camera. Today I do. Other days I look a little better. Oh. Look at that haze by the camera. That haze. Look at that haze. So direct light makes it. That's good. Yeah. Okay. Cool. I'm messing with it, but anyway. Enough of that. That was BS. I was close. I was not close. I had some right ideas though. Only keeping what wasn't a duplicate. Yeah, but the way I did it was bad. So recursion was not the way to do it. Yeah. Not